Welcome, everyone. Thank you for joining the Ceratec webinar, Simulating Drop Loads Impact on a Structure with Femap and NX NASTRAN. I would now like to introduce John LaCour, Ceratec's application engineer professional who is based out of Texas. John, you can take it from here.
Hello, this is John LaCour, and what I'm going to be talking about today is impact loads. I started first I came out of the aerospace world, and I worked shuttle and worked space station, and we did impact loads on the space station. Impact loads due to modules being connected together, and there's a robotic arm on the orbiter, and the space station actually takes the modules and puts them together, and it actually puts them together quite nice and slow, but sometimes there is conditions that we had to simulate. But one of the biggest impacts we had to do is the Soyuz coming in and docking, and it actually has to come in and impact the space station to lock in. So I was doing this probably back in 1996. So NASTRAN has a long history of doing impact loads. And so today, this is kind of our typical agenda here, but today I'm going to simulate a impact load using NX NASTRAN Transient Solution. To do an impact analysis, you need to move to a transient solution. Years ago, when computers were slow and we didn't have a lot of memory, we could kind of do it with a static solution, but it's just really not a thing that you want to do today. I could and will in the future more complicated solutions where there is a contact solution, and you'll see why we would potentially want to use a nonlinear. You'll also see that you can do it with a linear transient solution. And I want to say at this point, I intend to show the linear and the nonlinear solutions, but I just could not squeeze both of them into a 30-minute webinar. And so in the future, and I believe it's February 28th, I'll move to the nonlinear solution for contact loads with NX NASTRAN. Today, I'm going to the object I'm going to use for contact will be modeled with rigid elements. What I'll do is I'll demonstrate to you the difference, or show you the difference between RBE2s and RBE3 elements to model the impact object. This can apply to anything. I mean, using rigid elements to show you how they work and how you can use them to model masses. And today, this will be the simplest solution that you can use, and it actually will give you good results in the simplest solution and the transient solution. And so, here's what I'm going to do in simplest terms. I'm going to drop a box, a theoretical rectangular box. It's going to be modeled with rigid elements, and you'll see it in just a minute. So here's in the simplest terms, my box suspended, being held in the air. I got the object. There's the contact surface, and it's separated by some distance x. Okay. So right now, my conditions are: I have acceleration, I have a distance of x, and velocity of 0. Okay. Now I'm going to let the box go. Why you would want to do this is sometimes when you place items together, there is no other way but to have an impact. They have to release it and let it go, and you want to assess what the impact will be. When other things fall, and when they fall, it wasn't designed for that fall, and so you want to go back and assess, was the hardware damaged from the fall? And I'm going to give you a little heads up for what's coming in the future. Is with the Apollo 13, when that was, remember, it blew up. For those who haven't seen the movie or don't know the history, but Apollo 13 going to the moon, the fuel cells blew up. And why did they blow up? Well, I could go through the long scenario, but it happened because they accidentally dropped a tank set, the fuel cell tank set, and they didn't assess if that potentially damaged the tank. And they said, we don't see it, and therefore it's okay. And it ultimately tailed intrusion on the way to the moon. About that in the future. Okay, so let me move on. So now my object has been released. It's going to make contact with the surface. And here's my conditions. I again have acceleration here. I've multiplied it. I'm using the English system, but because my measurements are in inches, I have to convert this acceleration from 32.2 feet per second squared to inches per second squared. And my condition over here is now the distance x is 0. Okay, and so the only thing I need is at this point, when it just makes contact, I have a velocity. Okay, and so I just went and used the basic equations of motion to determine what that velocity at impact would be. And so here's my r value, and I used x over here. So it's 1, and my initial velocity when it was being suspended was 0. So it's really 2 times acceleration times that distance. And here, it's 0 velocity, acceleration, distance is 1, and the velocity at contact will be 27.8 inches per second. Okay, so now I'm ready to go. And this is going to be known as initial condition. Okay, so let me step out of my presentation and let me move over here to Femap. Okay, here we go. So here's what I'm going to be dropping an object on, mass on. But before I go any further, I want to talk about how the RBE2s. And so we can see I have this modeled all with plate elements. And what I'm going to do, it kind of gets, when I put stresses on here, it kind of gets showing the grids. It kind of covers things up. So I'm going to click that so we can turn those grids off. And so I'm going to put a mass on here. I'm going to drop a mass. So there's my mass. I've just turned my mass on. It's sitting up here. Okay. And I need to connect it to the surface. And this is made of surfaces and meshed. I meshed the surfaces. So what I'm going to do is I'm going to connect the rigid element to the surface here. Okay, and this is an RBE2. And what an RBE2 does is it will take all these degrees of freedom, and all these degrees of freedom, and it will couple it to this point right here, thus making this area a very stiff area. And if you drop a very stiff box, that might be exactly the proper modeling. This will probably give you higher stresses, and which is okay, but the ultimate answer it might be, did it break, did it not break? Okay, so this will give you, make this area very rigid right here, and I've already run this model, and so I'm going to come over here, and I'm going to turn on the stresses. Okay, I'm going to turn on the stresses, and then I'm going to turn on displacements, so we can look at the displacements. And this is a static run. What I'm trying to do is demonstrate what the RBE2 does. And so then I'm going to come in here, and I'm going to turn off my rigid elements. And you can see here, there's not a lot of stress here, and that's the reason why it's coupled all this together to that one point and made this area very stiff right here. Let's move to an RBE3. Here's my same structure. I'm going to put my mass up here. I'm going to turn on my RBE3s. Okay, I'm going to come in here and turn on the displacement. I'm going to turn on the stresses. And the first thing you might notice is the stresses actually go up, and why it's more flexible in this area. And of course, that's where the load's being applied. And actually, you can see that because I'm going to come over here and turn my rigid elements off, and you see how it's flexing inside here. And the reason why is instead of coupling all the degrees of freedom to this point, it's taking and placing all the mass properties down on this surface, and this is being taken out of the solution set. That's the reason. Okay, so this would be kind of if you're dropping, a big blob of Jello, and in some cases, what's being dropped onto here might not have stiffness, and this might be the proper solution when it doesn't have stiffness, So we can see so now you can see the difference between the RBE2 and the RBE3. So let's now move on to an impact. And so here's my structure again. okay? Those other transient solutions, all right? So what I'm going to do here is, again, I already have this set up. I already have my mass, and I already have my rigid, and I'm actually using RBE3, which is like dropping jello, okay? And I want to run a transient solution here. So my conditions are, I have acceleration. I need to apply the load, okay? So here is, I've just applied acceleration to the body load. This will be a continuous acceleration, okay? And so the other one is a velocity. This is, I have my velocity in here, and I can come in here and say edit, and you can kind of see that's the number that I computed there. It is in the negative y direction that it's moving. You see my coordinate system here. But this velocity only exists at contact. After that, the velocity will change, and it will change according to the energy transfer from the mass moving into the structure. And so therefore, this is an initial condition that I'm being placed. Okay, so how do I model? I have my structure, have my masses, have everything going. Now I need to apply this as initial condition. That will be done in the analysis manager. And let me open this up. And your boundary conditions is where you apply this. And if I open this up here, you'll see I have this untitled, my constraints, which are on the back side right here. And then I have my gravity load, and I have my velocity load, and I put that into the initial condition. That velocity will only apply initially, and then after that, the velocity will be it will be defined how the structure behaves. But the gravity will be constant. Okay. So here we're ready to go. I'm going to tell you, since this is a transient load, the velocity is a one-time thing at contact, and the acceleration is continuous. And I'll show you time. So I had to define a function here that takes it through all the time of the simulation. And if I didn't, I do not think it would run, because it needs to know what the load is being applied at any time during the simulation. So now we're ready to go. I applied a velocity. It has an acceleration, initial velocity in this direction. I can hit the run button, which I won't do because I've already hit the run button, and it takes a little time to run. And so here is the output results here, right here. And this might be worth looking at initially, but in looking at the results, I want to look at my plot. Now I'm working in Femap 11 now, and it has a new nice feature here. If you've looked at the plot function on earlier versions, 10.3.1 and earlier, it was kind of a little pain to use, but it was usable. Sometimes better to take it out into an Excel spreadsheet to make it look better. But now Femap 11 has a new feature called a new plotting feature, and I think it's very nice, very similar to Excel spreadsheets. And so what we have here, what I have plotted is the displacement of this point here. This if we come down here, if you can see down in here, this node point, I'm plotting the displacement of this node point in the y direction. Okay, and what I'm trying to find out is where the maximum deflection is, and that's probably going to cause the highest stresses. I have 100 cases here. I actually ran 1,000, but I said only save every 10 load cases, every 10 steps. So it's really painstaking to go through every one of these and look at it. And this is a nice clean model. It could be, I would need 1,000 on a more complex model to look at. So what you do is you would bring up some points. Of course, this is very simple how it's being applied. And so I'm going to look for this point, and I'm going to find out where the maximum displacement is. That's going to be an indication where the highest stresses are. So over here, I'm going to come and turn on my displacements and turn on my stresses. And we're right now at 1. That's nothing at time 0. Nothing's happened. So we can see the stress really pop up here, and we can see the displacement. And so I can just keep going through this, and I can see at point, even though this I can see it actually right early on. I'm getting high stresses right here and high displacements. And a matter of fact, at 0.02, it's my stresses are starting to fall off. If I come on over here to looking at this, probably 13, you can see my stresses have fallen way off. And so right at the initial impact, I had probably the highest stresses. Now, the question is where, I'm looking at this and I see this high stress value, and if I put it in this position and turn it around, it looks like the whole structure is just sitting there doing nothing. But actually, what's happening, it's at the initial contact, and the stresses or the loads are being propagating through the structure, and I have an initial high stress right at the area of contact right here. I have a little high stress right here, but not a lot. It might be past, well, it's actually in the 1,000, but this is like 40,000 right here at initial contact. So as I go through this thing, you'll see the stresses start to radiate out from the impact. And as I get past this and we start coming up here, way up there, we see the stresses are starting to radiate. Actually, we've gone past that. You see the stresses are starting to radiate down in this area. And while we still have a little high stress here, because it is the contact here, and the energy is actually that's going into the structure going through right here. We're still going to see high stresses, but we can see as the energy goes into the structure that the stress is down. And so for a high, for a lot of degrees of freedom or a lot of load cases, this could be a pain to go through here. And so maybe I would want a quick answer is what is the highest stress? Okay. And so I can actually do that. I can come over here and come to results. This is a new feature in Femap 11, and I can envelope it. And I say find the max values. And it will come in here to all these and go through all this and find the max value for all these time steps here. I've already run it. So it takes a couple of minutes, maybe 3-4 minutes for it to go through this, through all these stresses. And again, I'm looking at von Mies stress here, so I ask for the maximum. And so what I can do is I can come down here and click on this, and I can see the maximum stresses here. And if I want to really find out if I have exceeded the yield, or how much I've exceeded the yield, I can come over here to my post-processing toolbox, and I do have the deformation actually is turned on, but it's I probably need to turn up a higher percentage of the model, but that's not important here. What I can do is come in here to my contours and come to my criteria, and slide this down, and set a limit. Find out what's above, 20,000. This is 20,000 or 20 KSI, and we can see it's these two, probably just the top of these beams right here that are actually getting the highest stresses. Now, if we want to see what really the impact, if I could use that, I can go ahead and turn this back on with no limits. And what I'm going to do is my max is here, and I can go back and look at the difference here. This is right here. This is the difference in stresses due to the impact. And another way I can check my model, I'm going to see if this is, really kind of giving me a realistic simulation dynamic model. And so it is a function of the mode shapes, so the dynamic structure. But what I can do is I can come over here, and I'm going to take the criteria back off. And I can come back here, and I want to come over here. I want to see where, when all the energy has been damped out, you can see this damping that's taking place right here. At some point, all this kinetic energy has been damped out, and it goes to a static solution. And so I want to come over and look at this, at what's happening statically here. And so here we can see it's pretty much damped out as I'm clicking through this. These values don't change. And so here's my static solution, solution 101, with a load on it, no velocity. And we see we have, it looks like a maximum of 905. I can come over here. Here's a point. I'm way down in this area where all the energy from that velocity has been damped out, even by damping. And now we're at a static solution, and it's almost like 920. So it's just, it's probably 15 psi off, very close. So actually, that's actually not a bad solution. But what we can see here is the contribution from the drop was a large contribution, but the contribution was in a very local area. And it's this area right here, which kind of makes sense. If you drop something on a platform, it's very common to see a dent in the platform, but it doesn't usually break the platform. Usually doesn't. Sometimes it does, but in a lot of cases, you drop a small item that's heavy, you dent it. That's what this simulation has just said. It's dented the platform. Okay. So this is a transient solution. It is not a nonlinear. That is, it's not a nonlinear. A nonlinear solution might be better, and I'm going to say might. And what a nonlinear would do is I could use something like gap elements where it could break contact. And actually, as it drops and makes contact and then springs back up, it's potentially the platform, the object that's been dropped will come separate, and you would not see this rise right up here. You'd probably see something, a more complicated vibration that's going on here as this thing's jumping off the surface and then making contact with the surface. But as you can see, probably the highest stresses are still happening over here. If you're really wanting to see the total simulation, this isn't going to do it. But if you want to see the maximum stresses, this is probably going to show you the maximum stresses. And in our next webinar, when I go into the nonlinear contact, we're going to see if this is how well this is giving us the maximum stresses. So I'm going to go back to my presentation to wrap this up. And here's our conclusion. Okay, so the transient solution with initial conditions will only run in a direct solution. I didn't tell you that, but when you do initial conditions, you can only use direct solution. You can't use the modal solution. In modal, it allows you to significantly reduce the degrees of freedom that are going into the solution. So because you're using direct, you can't reduce it. Probably could reduce it with Gaussian reduction. That's a very complicated thing to do, and I wouldn't recommend it. So you really need to watch your degrees of freedom that you're using, because you'll only be allowed to use direct solution. This simulation considers the object sticking to the platform, which doesn't happen. But again, I'm looking for the max stress, and the max stress happens at the contact, and as it's cycling down and not cycling up, because as it's coming up, damping will take energy out of it, and as we saw, as it came back up, a lot of energy had been taken out of it from the damping. Simulation does show a higher stress due to the impact, so that's good to see there. This was a good solution for stress, because it did show me if the question was, did it break, did it bend? The answer, it gave you the answer, yes, you bent the structure. However, this solution is inadequate for life assessment. And life assessment, you need cycle counts. Okay, so if I went ahead and used this solution for life, you need to go ahead and continue on through the sim as the thing is potentially breaking contact with the surface, and you can't do an adequate cycle count with this. You'll have to go to nonlinear. One other thing is this is a dynamic simulation. One must fully understand NX dynamics or dynamics in general to get good results, because Femap allows you to set up an easy dynamic solution. But if you don't know what you're doing, you can easily produce bad results. And I want to let you know, in the future, I'll be demonstrating a nonlinear solution for impact. And the reason why is I didn't have time in this 20-25 minute time frame to do that. So that's the conclusion. I would like to now open up for questions.
Thank you, John. We'll now begin the question and answer session. If you have a question, please enter it at this time in your GoToWebinar control panel. And also, as a reminder, we'll be hosting the second part of this webinar on February 28th, so make sure you register for that. And I'd like to give the audience a heads up that when you leave the webinar, a survey will pop up on your screen. This will give you the opportunity to provide your opinion of today's presentation and ask additional questions offline if you prefer. John, I do have quite a few questions, so we'll get started. The first one's a two-part question. I noticed the acceleration load reference a function, and what is the function? And what is the mass of the mass element used in the example?
Okay, the acceleration is the acceleration that we're experiencing right now. Okay, we had the acceleration was 32.2 times, got it to inches, and it just have to be consistent. Is constant. I'm sitting in my chair, you're sitting in your chair, or standing, I don't know, but it is a constant. So if you would have gone to the function that I had there, it is a straight line. It is 1 all the way across. Okay, and so that's the acceleration function, a constant acceleration. And what was the second part of that question? Oh,
what is mass?
It was what is a mass element?
What is the mass of the mass element used in the example? Okay,
it's 10. It's 10. I was just I used 10. It's I was just this isn't a real situation. I created this on the fly, and I pulled out values out of my hip pocket and put in there, and so I used 10. So that would probably be, that's 10. 10. It'd be inch slugs, something like that. Again, It has to be inches. I mean, it has to be, your units have to be consistent. Slugs are in feet, so I had to convert slugs to inch slugs, something like that.
Great. Another question. This is like dropping a rock on your structure. What about dropping your structure on the ground? Mass equals infinite, RBEs to the entire surface.
You can do that, and that actually would be a good topic for a future webinar. I will do, in the next webinar, I'm going to do a nonlinear drop and do exactly that and show you how to drop it onto a rigid structure. It is possible, well, you're probably going to have to do it nonlinear, okay, because you're having large displacements as I'm dropping that structure. And a matter of fact, in the next webinar, when I go nonlinear, that's exactly what I'm going to do. I'm going to drop a structure and show you how to do that onto a rigid contact surface.
Great. All right, another question. Can you comment on the differences between this approach and an explicit solution?
The explicit solution, meaning the nonlinear, would be, if I was, what you will probably see in the next one where I go nonlinear is that I'm going to have a contact surface there. The basic nonlinear, you can use gap elements, okay? So with that, the difference in the solution would be is in a gap element is that the spring constant, when it makes contact, the springs will get very stiff and you'll have a hard contact. And then when it actually breaks contact, then you're going to have very low spring stiffness, which is essentially no stiffness, and it will allow it to come back off. Okay. Now I could go for the advanced nonlinear, which makes it a lot easier actually. We're using a contact surface. You can use the connect, and you can actually have it impact the connect surface. So the difference is going to be in the cycle count. I have been running. I'm in the process of running some now, but I suspect the max load is going to be pretty close to this direct linear solution.
Okay, great. I will be combining two questions regarding damping. Do your material properties include damping, and what type of damping did you use?
Okay, that's damping is the art of a dynamicist, and that I truly mean as art. You know, and this is I would consider a civil structure, and when I open up my steel manual, I haven't seen a damping term in there. Okay, so the damping I use I'm running a direct solution. If you're running modal, you could say it's 2%, 3% damping. When you go direct, it becomes kind of an art, in my opinion. So what I did is you have to pick the center frequency for the damping, and I chose the first mode shape, and that's the first mode, which is the primary mode, and it's the mode that I know will be excited when it makes impact. So I chose that as my primary damping, which was, I think, 47 hertz is about that mode that we saw there. And then what I did is I just kind of kept putting different damping values in there till I saw realistic damping. To be honest, the damping I saw that you saw today in that curve was probably a little bit over damped. And but the first number I put in there damped it. Well, the first several numbers I put in there, it damped it so heavily it passed critical damping. It didn't even cycle. It immediately went into a static solution. So I had to keep backing off the damping. And just to be honest with you, I think I used a damping factor of 1, which doesn't mean anything because it's 1 times the stiffness matrix is the damping value. So what you have to do as a dynamicist, you have to kind of keep putting different values of damping in there, and it will change based on the structure until you see some what you think is realistic damping. And what I do is I not so much the term underdamp, but I kind of look at the damping and then I back off of it, and that's the damping I use. There is no damping in a steel manual. There is no damping in a book. It is purely looking at the structure and changing the damping values until you think it's realistic.
Okay. I'm reading through these other questions. These two questions that I have are in reference to your example, wondering if they could download your example files and being able to access this bulk data file to reproduce this exercise on our own.
I have to check with the company, but I mean, let me check with our policy. You know, you're asking, can I give this model to the public? That'd be a policy question.
All right.
That I'd have to ask Ceratec people. I hope I can. If I can, I will.
Okay, wonderful. Okay, what NASTRAN solution method did you run to get this transient dynamic analysis? Was it SOL 109?
109.
109. Okay.
It's the linear transient.
Okay.
And what I did is I use Femap and I go where it says linear transient.
This will be the last question here that I'll be asking for you is we use MSC NASTRAN. Any specific difference between what you did in NX NASTRAN versus MSC NASTRAN?
Well, first I want to say shame on you for using. Just kidding. I really think the solutions. You know, it's a good product. I think the solutions. The solution between the NX NASTRAN static and transient dynamics are going to be fairly close. I do it with Femap, okay, and of course supporting the most current version of NX NASTRAN, and that is 8.5. Okay, and when you write an MSC deck from Femap, you're going to be writing an older deck, and I don't know what version that is. Okay, so the question is, will it produce the same results out of Femap? I don't know that question because I don't know what version of MSC Femap is going to write. But if you can use the current version of MSC and the current version of NX NASTRAN, which I did, I think you're going to see similar results.
Okay, great. Well, due to the limited time we have for these events, we can only show you certain features and benefits of the solution. But if you have any additional questions after our presentation or are interested in a one-on-one consultation or training options, please contact us at 949-481-3267, extension 2001, or email us at solutions@ceratechinc.com.